the very closest. In a galaxy of hundreds of billions, our solar system is a speck. Our stellar neighborhood is a speck. We are a speck within a speck. Between us and the rest of the universe lies an ocean of silence, a void that reminds us of our own insignificance. But to understand where we are going, we must first accept how small we really are. The Alpha Centauri system is just the beginning of a journey that spans the entire cosmos. From here, the distances only grow. The numbers become so large they lose all meaning. Yet, here we are, on our tiny pale blue dot, looking out and asking, what else is there? We are travelers on a journey through the infinite, and the next chapter is about to begin. Some questions seem too big to answer, but we're going to keep looking, because the speck matters.
Our solar system is inside a bubble of hot, thin gas called the local bubble. It's about 1,000 light years across. Inside it are about a dozen stars. The nearest ones are tens of trillions of kilometers away. This is what space is, not stars, not planets, empty. Vast, cold, silent emptiness. The stars are islands in an ocean of nothing. And we are on one of those islands. Beyond our sun's reach lies Proxima Centauri, a small red dwarf. Only 4.2 light years away, yet an unreachable distance for now. It is the closest neighbor we have in this cosmic void. Proxima orbits a binary pair, Alpha Centauri A and B, two brilliant suns similar to our own, dancing in the darkness. A triple star system that serves as our first galactic milestone. To cross this gap at light speed would take over 4 years. For our fastest probes, it is a journey of 70 millennia. Space is not just big, it is fundamentally disconnected. This void is not truly empty. It is filled with the interstellar medium, the breath of dying stars and the seeds of new ones. We are passing through a patch called the local interstellar cloud. Before we reach the void, we must pass through the Oort cloud, a trillion icy wanderers marking the graveyard of our solar system's birth. This is the final frontier before the true interstellar deep. Our sun is a traveler, moving through this bubble for 5 million years. A fleeting moment in galactic time. An accidental visitor in this void. Soon, we will leave the bubble behind, heading into the unknown. The void between stars defines us as much as the stars themselves. Solitary beacons in a dark, infinite ocean. Some questions seem too big to answer. We answer them anyway.
The universe is a vast expanse of mystery, but none so close as the home we call our own. To understand our place, we must first look at the grand architecture of the Milky Way. This is our galaxy. The Milky Way. At 100 light years, the stars begin to cluster. 1,000 light years out, the great spiral arms start to emerge from the darkness. 10,000 light years, the galactic center glows with the light of billions. 100,000 light years across, a colossal structure containing 100 to 400 billion stars. Our sun is just one of them, an ordinary star in an ordinary arm of an ordinary galaxy. But ordinary does not mean insignificant. It just means we are part of something much, much larger. We are not at the center of our galaxy, not even close. We're 27,000 light years from the center, tucked away in a quiet corner, in a minor spiral arm called the Orion Arm. Not special, not central, just another star. When you look up at the night sky, everything you see feels infinite, but it's an illusion. Every star you can see with your naked eye is within just 1,000 light years of Earth. That's only 1% of the diameter of our galaxy, a tiny fraction of the whole. The rest of the galaxy, 99% of it, is invisible to us without the aid of telescopes. Hidden behind clouds of gas and dust, billions of worlds remain unseen. At the very heart of this vast structure lies a monster, a supermassive black hole. With the mass of 4 million suns, it holds the entire galaxy in a gravitational embrace. But stars and black holes are only part of the story. There is an invisible skeleton here. Dark matter. It outweighs all the stars and planets 10 to 1. Silent, invisible, essential. Our galaxy is not alone. It's part of a small family known as the Local Group. In 4 billion years, we will collide with our neighbor, Andromeda, to form a new, giant home. In this vastness, our smallness is not a tragedy. It's a perspective. A reminder that we are part of a grand, spinning masterpiece of light and gravity. This is our home, a tiny dot in a sea of stars. Join us as we continue to explore the impossible.
The Milky Way is not alone. It's part of the Local Group, 54 galaxies bound together by gravity. The largest is Andromeda, 2.5 million light years away. It's heading toward us. In 4.5 billion years, we will collide. This massive merger will create a new giant elliptical galaxy. This group spans 10 million light years, a small family in a much larger cosmic neighborhood. We have smaller companions too, the Magellanic Clouds. They're visible from the southern hemisphere. They've been our neighbors for billions of years, but their proximity comes at a cost. They're slowly being torn apart by our galaxy's gravity, eventually becoming part of our own. The local group is just a small part of the Virgo cluster, a swarm of over 1,300 galaxies. At its center is M87, a giant elliptical galaxy with a black hole 6.5 billion times the mass of our Sun. This cluster is the heart of our local cosmic city, exerting a massive gravitational pull on everything around it. The Virgo cluster is part of the Virgo supercluster, thousands of galaxies spanning 110 million light years. Our local group is just a tiny suburb in this vast cosmic city, barely a footnote in the grand scale. But even this city of cities has a mysterious force guiding its motion. There's something strange about the Virgo supercluster. Everything is flowing toward a point called the Great Attractor. We can't see it, it's hidden behind our galaxy, but its gravity is pulling us. Something massive is out there. We don't know what it is. It's a mystery that reminds us how much of the universe remains in the shadows. The Virgo supercluster is part of an even larger structure called Laniakea, immeasurable heaven in Hawaiian. It spans 520 million light years. It contains 100,000 galaxies. Our local group is a speck within it. The largest structure in the universe is the cosmic web. Filaments of galaxies stretching across billions of light years, separated by voids where almost nothing exists. This is the architecture of everything, and we are a speck in a speck in a speck. This is everything we can see. The observable universe, 93 billion light years across, 2 trillion galaxies. Each galaxy has billions of stars. Each star may have planets. The numbers are so vast that they lose meaning. In 2004, astronomers pointed Hubble at a tiny patch of sky, the size of a grain of sand held at arm's length. The observable universe is not the whole universe. It's just the part we can see. The light from beyond hasn't had time to reach us, and it may never reach us because the universe is expanding faster than light can travel. If cosmic inflation happened, and the evidence suggests it did, then the entire universe is at least 10 to the 23rd times larger than the observable universe. That's a 1 followed by 23 zeros. At that scale, our observable universe is a single atom in a body the size of the observable universe. We are not just small, we are smaller than we can imagine. Some theories go further. Inflation might be eternal, happening forever in different regions. If that's true, then our universe is just one bubble in an infinite sea of bubble universes, each with its own physical laws, each potentially infinite, and we are in one of them. Let's add it up. A human is 1.8 meters tall. Earth is 12,742 kilometers across. The solar system is 1.5 light years across. The Milky Way is 100,000 light years across. The observable universe is 93 billion light years across, and the unobservable universe may be 10 to the 23rd times larger. We are not just small, we are not just insignificant, we are almost nothing. If the entire universe were the size of a grain of sand, the Milky Way would be a speck of dust on that grain. The Earth would be a subatomic particle. You would be smaller than an atom. And that's if the universe is finite. If it's infinite, then we are literally nothing. This is the disturbing truth. In the grand scale of the cosmos, we are not even a pixel. Every human who ever lived, every war, every love, every dream, all of it on a mote of dust suspended in a sunbeam. The universe doesn't know we're here. It doesn't care, and it never will. But here's the thing. Size doesn't matter. Significance isn't measured in light years. It's measured in awareness, in consciousness, in the ability to look at the cosmos and ask, what am I? Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician,
Every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. We are small, smaller than small. In the cosmic scale, we are less than a pixel, but we are the part of the universe that can see itself. We are the part that can wonder. We are the part that can ask. That is not nothing. That is everything. We are small, infinitely small, but we are significant because we are aware, because we can look at the universe and understand it, just a little, because we can ask questions, because we can wonder. The universe is vast beyond imagination, but we are the part of it that can say, I am here. And that is everything. Thank you for joining us on this journey through scale. If it changed your perspective, share it with someone who needs to be reminded how big the universe is and how small we are. Comment below. At what point in this journey did you feel the most disturbed?
What if we could see space-time? Not just imagine it in equations, not just trace it in diagrams, but see it, feel it, move through it. What would it look like? How would it behave? What secrets would it reveal? This is not a documentary about physics. This is more than just physics. This is an experience, a journey into the fabric of reality itself. We are all swimming in an ocean we cannot see. Every moment of our lives, we move through space-time. We are carried by it, shaped by it, bound by it. But we cannot perceive it directly. It is invisible, like a fish that cannot see the water it swims in. But what if we could? What if we could open our eyes to the fabric of reality itself? In this documentary, we will open those eyes. We will visualize space-time as it truly is. A dynamic, flowing, living fabric that bends around every particle of matter, that ripples with every cosmic collision, that carries us through the universe at the speed of light. We will see it around a star, around a black hole, around your own body. This is general relativity, made visible. For centuries, we saw the universe through Isaac Newton's eyes. Space was a vast, empty stage, fixed, absolute, unchanging. Time was a universal clock, ticking the same for everyone, everywhere. If you moved through space. Time just passed. Simple, intuitive, wrong. Absolute space in its own nature remains always similar and immovable. In Newton's universe, space was a rigid grid. You could travel anywhere, and the grid stayed the same. Time was a river flowing at a constant speed. Nothing could change them. This was the world we knew for 200 years. Then a young patent clerk in Switzerland had an idea that would shatter it. The cracks in Newton's universe appeared in the 19th century. Scientists noticed something strange. The speed of light seemed to be constant, no matter how fast you were moving. That shouldn't happen. If you shine a light from a moving train, shouldn't it go faster? It didn't. Something was wrong. Something was missing. Something was about to change everything.
In 1905, a 26-year-old Albert Einstein had a thought experiment. What would it be like to ride a beam of light? That question led him to a radical conclusion. The speed of light is constant for all observers. This simple idea had a mind-bending consequence. Time is not absolute. If you move very fast, time slows down for you. Einstein asked, what would I see if I rode a beam of light? If you travel at 90% of light speed, time slows by half. At 99.9%, it slows by a factor of 22. At 99.9999%, years on Earth pass like days for you. Time is not a universal river. It is a flexible fabric that can be stretched and compressed by motion. They are inextricably linked. Einstein realized that space and time were not separate. They were woven together into a single, four-dimensional fabric. He called it space-time. Every event in the universe has a location in space-time. 3 coordinates for space, 1 for time. You cannot move through space without moving through time. As Hermann Minkowski said, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve reality. To understand space-time, we use a simple analogy. Imagine a rubber sheet. Place a heavy ball on it. The sheet dips. That dip is gravity. A smaller ball rolls toward the larger one, not because it's being pulled, but because it's simply following the curve of the sheet. Gravity is geometry. Einstein summarized it. Matter tells space-time how to curve. Space-time tells matter how to move. This is the essence of his vision. But space-time is not a 2D sheet. It is a 3D fabric that wraps around everything. A massive star creates a 3D warp in the space around it, and that warp is what we feel as gravity. If we could see space-time, this is what we would see. A star is not a point of light in empty space. It is a weight on the fabric of reality, bending it, warping it. And everything around it, planets, comets, light itself, is simply following those curves. Exploring the impossible, one curve at a time. Some questions seem too big to answer. We answer them anyway. Join us as we unravel the mysteries of the universe.
Earth is not just a rock floating in space. It is a dent in the fabric of reality, a warp in space-time, and you are inside that warp. The sun's warp is enormous. Planets don't orbit because of a mysterious force. They are simply rolling along the curve of space-time like marbles in a funnel. If you could see space-time, you'd see that time is not uniform. Near massive objects, the fabric is stretched, and time itself flows slower. It's a fact. A clock at sea level ticks slower than one on a mountain. Your head is actually slightly older than your feet. Now imagine a neutron star. Its warp is so extreme that time passes at half the rate. 1 year, there is 2 years elsewhere in the universe. Time dilation is not just science fiction. It is a fundamental fact of our universe. If we could see space-time, we would see it happening everywhere.
Some questions seem too big to answer. We answer them anyway. If we could see space-time around Earth, we would see something surprising. It is not uniform. Earth's gravity varies from place to place. Mountains create tiny warps. Ocean trenches create dips. The geoid, the shape of Earth's gravitational field, is a lumpy, uneven landscape of space-time. Every satellite in orbit is navigating this warp. They follow the curves like marbles rolling in a bowl. The orbits are not circles or ellipses in empty space. They are paths through curved space-time. GPS satellites have to account for both the warp of Earth and the time dilation of their motion. Earth's rotation does something even more subtle. It drags space-time with it. This is called frame dragging. As Earth spins, it twists the fabric of space-time around it like stirring honey with a spoon. This effect has been measured by satellites. If we could see space-time, we would see Earth's warp slowly rotating. Now we come to the ultimate warp, a black hole. Here, space-time is stretched to its limit. Near the event horizon, the fabric is falling inward faster than light itself. Light can travel outward at the speed of light, but the fabric is moving inward even faster. So light cannot escape. The event horizon is the point of no return. Space-time is falling into the black hole faster than light. That's why nothing can escape. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. What you see is not the black hole itself, it is the silhouette of space-time warped beyond return. The glowing ring is light from matter heated to billions of degrees. This is what space-time looks like at its most extreme. If you fell toward a black hole, you would experience the ultimate expression of space-time curvature, spaghettification. The gravity at your feet would be much stronger than at your head. You would be stretched into a long, thin strand of matter. This is not a metaphor. This is what happens when space-time is stretched to its breaking point. Inside the event horizon, space-time becomes something else entirely. Time and space swap roles. What was space becomes time. What was time becomes space. The singularity at the center is where space-time ends, where our understanding ends, where the universe hides its deepest secrets.
If space-time is a fabric, then violent events should create ripples, gravitational waves. In 2015, scientists at LIGO detected these ripples for the first time. From two black holes merging 1.3 billion light-years away, if we could see space-time, we would see these waves passing through us constantly. LIGO scientists stated, "We have detected gravitational waves. We did it. Every moment, the fabric of space-time is being stretched and compressed by distant cosmic collisions. These waves are passing through you right now. The effect is tiny, smaller than a proton, but it is real. When two black holes merge, they release more energy in a fraction of a second than all the stars in the universe combined. That energy is not light. It is waves in space-time itself. They stretch and compress space as they pass. In the GW1 Fanvo 914 event, 3 solar masses were converted entirely into gravitational waves. If we could see space-time, we would see these ripples as clearly as waves on an ocean. The effect on Earth is smaller than a proton, but it means the universe is breathing. If we could see space-time on the largest scale, we would see the cosmic web. The distribution of galaxies is not random. They cluster along filaments of dark matter, and those filaments warp space-time. The universe is not a flat, empty void. It is a complex, curved landscape of peaks and valleys, hundreds of millions of light-years across. Our own local group is being pulled toward a region called the Great Attractor. Something massive is warping space-time. Galaxies are flowing toward it like water down a drain. We cannot see it directly, but its warp is unmistakable. On the largest scale, the shape of space-time determines our fate. Is it flat, like a sheet? Is it positively curved, like a sphere, where traveling in a straight line brings you back? Or is it negatively curved, like a saddle? Measurements show it is nearly flat, but the answer is not yet certain. Some questions seem too big to answer. We answer them anyway.
At the smallest scales, the Planck scale, a trillion times smaller than a proton, space-time is not smooth. It is a frothing, bubbling foam. Quantum fluctuations constantly create and destroy tiny bubbles of space-time. This is the quantum foam. If we could see space-time at this scale, we would see a universe in constant flux. The scales here are unimaginable. The Planck length, 1.6 is 10 to 35 meters. It is the smallest possible unit of distance. And Planck time, 5.4 x 10^44 seconds, the smallest tick of the cosmic clock. Beyond this, physics breaks down. This bubbling foundation is where space and time itself are born. In this foam, particles pop into existence and vanish. They borrow energy from space-time itself, then return it. This is not empty space. It is the seething, boiling foundation of reality, and we are made from it. If space-time is a four-dimensional fabric, why does time feel different from space? Why can we move left and right but not backward in time? This is the arrow of time. And it is one of the deepest mysteries in physics, why the past is gone and the future is yet to come. The arrow of time comes from thermodynamics, the flow of heat, the increase of disorder. In the beginning, the universe was highly ordered. Since then, it has been unwinding. That unwinding is what we experience as time. The arrow of time is the memory of the Big Bang. If you could see space-time from outside, you would see a human life as a single continuous line, a world line. Every moment of your existence from birth to death is already there in the fabric. We experience it one moment at a time, but in space-time, it is all there, all at once. Some questions seem too big to answer. We answer them anyway. Follow for more.
We have journeyed through space-time, from the smallest quantum foam to the largest cosmic web. We have seen the fabric that holds everything together. We have seen it warp around stars. We have seen it ripple with gravitational waves. We have seen it tear around black holes. We have seen where it ends. The fabric is still there, invisible as always, but now we know it. We have seen it. And now we return to Earth, to a person looking up at the stars. It is not empty space. It is not separate from us. It is the medium we move through, the medium we are made of. We are not in space-time. We are part of it. As Einstein once said, the distinction between past, present, and future is only a stubbornly persistent illusion. The next time you look at the stars, remember, you are not looking through empty space. You are looking through the fabric of reality itself. It bends around you. It flows through you. You are made of it, and you are part of it. This is space-time. This is the universe. This is where you live. You are here. You are part of this fabric. Thank you for joining us on this journey through space-time. If it changed your perspective, share it with someone who needs to see the fabric of reality. Comment below. What would you want to see if you could look at space-time? Some questions seem too big to answer. We answer them anyway.
Welcome to this in-depth update from NASA. Today, we explore groundbreaking missions shaping our future. On February 13th, a new crew arrived at the International Space Station. This team replaced astronauts evacuated due to a medical emergency. Meet the crew: Jessica Meir and Jack Hathaway from NASA, Sophie Adenauer from France, and Andrei Fedyaev from Russia, pioneers of this historic journey. This crewed flight marks a milestone, the first since Apollo, to orbit the moon, paving the way for Artemis missions. Weeks of intensive training ensure the crew is prepared. Every detail is practiced for a safe journey. Back on Earth, mission control teams monitor every detail, tracking data, ensuring all systems function perfectly. NASA is also launching 2 new Earth-observing satellites, Strive and Edge, designed to monitor climate change and natural disasters in real time. Strive will focus on extreme environments, providing early warning systems for floods, wildfires, and storms. Edge will monitor long-term climate patterns, offering insights for future missions to the Moon and Mars. Despite these advances, a budget freeze has paused over 15 scientific missions, pending further funding approval. Even the Chandra X-ray Observatory faces delays, as budget constraints force a pause on key science missions. A groundbreaking discovery: ammonia detected on Europa, hinting at possible habitability beneath its ice. The detection of ammonia strongly suggests the presence of a vast subsurface ocean. This discovery fuels hopes of life beyond Earth. Scientists now plan follow-up missions to probe deeper. As Artemis takes us back to the Moon, Europa exploration may soon follow. Two frontiers of discovery. These new satellites will affect our daily lives, improving disaster response and climate predictions. While new missions excite, funding challenges put some science projects on hold, awaiting further approval. Despite hurdles, NASA forges ahead, building new partnerships, new technologies, and new dreams. Public engagement grows. Students, scientists, and dreamers alike follow every step of NASA's progress. Stay with us on this cosmic journey. NASA will continue to reach for the stars and bring the universe closer to home. Across the globe, audiences are tuning in, inspired by each milestone in NASA's journey. Students everywhere are dreaming bigger. Many now aspire to careers in space exploration. NASA scientists are reaching out, bringing space knowledge to classrooms, fairs, and community events. Mark your calendars. Upcoming launches like Artemis II are set for later this year, a landmark step in space exploration. NASA's success depends on global partnerships. Together, we push beyond boundaries. Each mission pushes technology forward, new materials, new propulsion, and new possibilities. As NASA explores new frontiers, space tourism may also become a reality in the coming decade. NASA's educational programs empower a new generation, offering free courses in STEM fields. With these satellites, we can better understand and act on Earth's climate crisis, ensuring a healthier planet. From the ISS crew to new satellites, every achievement brings us closer to understanding our universe. The future of human spaceflight is vast. Mars, deep space, and beyond, all within our reach. Stay connected with NASA. Visit their website and follow them as we continue reaching for the stars. NASA's ambitions reach far beyond Earth, deep space probes that will one day leave our solar neighborhood. Future missions envision human habitats on Mars, self-sufficient, sustainable, and ready for pioneers. The James Webb Space Telescope is unlocking cosmic secrets, peering back at the universe's earliest moments. Though paused, Chandra's legacy endures, its discoveries reshaping our understanding of black holes and stars. Space research also focuses on astronaut health, understanding how microgravity affects the human body. From space, we see Earth as one, our fragile home, interconnected with every step we take beyond. Women like Jessica Meir and Sophia Adenauer are breaking barriers, leading the way in space. Every mission inspires the next generation, those who will one day reach farther than we ever dreamed. NASA's legacy is built on decades of courage, each mission laying the groundwork for the next. As we look up tonight, remember, NASA is not just about rockets. It's about dreams reaching the stars. Follow NASA online, be part of the journey, and help shape the future of space. Until next time, we continue this adventure, exploring, discovering, and dreaming together. From space, we see our home in new light. Every nation, every ocean, connected in one planet. NASA is also leading in green innovation, developing sustainable technologies for Earth and space. Women engineers are driving innovation at NASA, bringing fresh perspectives to every project. From lunar orbit, Earth looks so fragile, this pale blue dot, uniting us all in one vast cosmos. On the ISS, every day brings new discoveries, from plant growth to materials science, pushing boundaries. Strive and Edge will monitor Earth's health, helping us respond to climate changes before it's too late. NASA's partnerships with private industry accelerate innovation, new rockets, new data, and new possibilities. NASA opens its treasure trove of data to the public, empowering researchers, students, and policymakers alike. In the next decade, space tourism may become a reality, with NASA paving the way. NASA reminds us, our journey is not just about leaving Earth, but about understanding where we fit in this vast universe. By sparking curiosity, NASA inspires kids to ask big questions about space, about Earth, about the future. Every launch takes us one step closer to new worlds, new technologies, and new hope. NASA reminds us that Earth is delicate. Our responsibility to protect it grows with every discovery in space. We need your innovation. As we reach for the stars, we also build a better future here on Earth. NASA promises to keep exploring, keep innovating, and keep dreaming for all of humanity. Thank you for joining us. Until next time, keep looking up, keep dreaming, and keep exploring.
Look up. On any given night, you might see it, a silent, glowing orb, our closest cosmic neighbor. For all of human history, the moon has been our companion, a source of light in the darkness, a keeper of time, and a canvas for our myths and dreams. But what is it really? This is the story of our moon. 250,000 miles away, that's about 30 Earths placed end to end, it orbits us. It's a world of stark contrasts. About a quarter the size of Earth, its gravity is just 1/6 of what you feel here. A place where daytime temperatures soar higher than boiling water, and nights plunge to -280 degrees Fahrenheit. A silent, airless, and lifeless world. And yet, it doesn't always look the same. Its beautiful, predictable dance through the sky gives us the phases. As it orbits us, the sun illuminates different parts of its face. From a slender crescent, a symbol of new beginnings, to the awe-inspiring full disk of the hunter's moon. This celestial ballet has been humanity's first clock, marking the passage of months and seasons. But the moon we see today wasn't always there. Ancient cultures told stories of its birth. But the true origin is a tale more violent and spectacular than any myth. It's a story of a cosmic catastrophe that happened over 4.5 billion years ago. Meet Theia, a rocky protoplanet from the early solar system. In a chaotic cosmic shooting gallery, its path crossed with that of the young Earth. The result wasn't a simple crash. It was a titanic glancing blow that vaporized Theia and a huge chunk of Earth's mantle, sending a cloud of molten rock and gas spinning out into space. For thousands of years, Earth wore a ring, but gravity is persistent. This massive disk of debris began to coalesce, pulling itself together piece by piece. In a cosmic blink of an eye, the material clumped into one object. Our moon was born. And in its infancy, it was incredibly close, 10 times closer than it is today, filling our skies as a gigantic, terrifying, and beautiful sight. This newborn moon was a ball of molten magma, a world of lava. As it slowly cooled over millions of years, lighter minerals floated to the surface, forming its primordial crust. This infant world was then relentlessly pummeled by leftover debris from the solar system's formation, a violent bombardment that would forever scar its face. This violent birth gave us a gift. The moon's powerful gravity pulls on our planet, creating the tides. As the moon orbits, it drags Earth's oceans with it, creating the rhythmic pulse of the seas. This daily ebb and flow may have been the perfect mixing pot for the complex chemistry of life, helping to move from the oceans onto land. When you look at the moon, you're seeing two different stories written on its face. The dark, smooth patches are called Maria, Latin for seas. Early astronomers mistook them for actual oceans. We now know they are vast, ancient lava plains. The brighter, heavily cratered regions are the lunar highlands, the original ancient crust. The Maria were born from violence. After the initial bombardment, giant asteroids smashed into the moon, creating enormous, deep basins. For millions of years afterward, magma from deep inside the moon pushed up through these weakened crustal cracks, flooding the basins and freezing into the dark, iron-rich rock we see today as the Man in the Moon. Look closely at the full moon. You'll see a bright, almost blinding crater near the bottom. That's Tycho. Its rays are streams of ejected material blasted out by a relatively recent impact, only 108 million years ago. And craters like Copernicus, with their magnificent terraced walls and central peaks, show us the incredible power of these impacts, forcing the lunar crust to rebound like a splash in a pond. But up close, the moon isn't rocky. It's covered in a layer of gray, dusty debris called regolith. For billions of years, micrometeorites, tiny specks of space dust, have been sandblasting the lunar surface at high speed.
This constant pounding has ground the rocks into a fine, sticky, and abrasive powder that clings to everything, a layer that perfectly preserves every footprint for millions of years. For millennia, we could only look and wonder. But in the 20th century, the moon became a destination. The Cold War's space race turned our gaze into a goal. First, robotic scouts were sent. In 1959, a Soviet spacecraft captured the first blurry images of the mysterious lunar far side, a hemisphere we never see from Earth. This set the stage for an audacious challenge. The Apollo missions were humanity's greatest adventure, a towering Saturn V rocket, more powerful than anything built before or since, hurled 3 men towards another world. After 3 days of travel, they entered lunar orbit. Then came the moment of truth. The lunar module, a fragile spider of a spacecraft, separated and began its powered descent to the surface. On July 20th, 1969, the world held its breath. The Eagle has landed. Then a ghostly figure descended a ladder and spoke words that will echo for eternity. That's one small step for a man, one giant leap for mankind. For the first time, a being from Earth stood on the surface of another world. Over 6 successful landings, 12 humans walked on the moon. They drove dune buggies across its plains, set up laser reflectors we still use today, and brought back 842 pounds of moon rock. Priceless geological treasures that continue to teach us about the origins of our solar system. And then, in 1972, we left. And for over 50 years, the moon has been silent, waiting for our return. But we are going back, not just to visit this time, but to stay. NASA's Artemis program aims to land the first woman and the first person of color on the moon. This time, we're building a space station called Gateway in lunar orbit, a pit stop for a new era of exploration. We will build habitats, learn to live off the land. We'll drill for water ice, the key to survival, which can be turned into drinking water, breathable oxygen, and even rocket fuel. The moon will become our proving ground, a harsh but perfect test bed for learning how to live on another world. From a mysterious light in our sky to a world we've touched, to a future home. Our moon is more than just a rock. It's a time capsule, a cosmic mirror, and our first step towards the stars. The journey that began with a look up is far from over. It's only just beginning. This is Alaknanda, a massive, grand design spiral galaxy located 12 billion light-years from Earth. At first glance, it looks ordinary, beautiful, but ordinary. But here's what makes it extraordinary. We're seeing it as it existed just 1.5 billion years after the Big Bang. According to everything astronomers thought they knew, this galaxy should not exist. In the early universe, galaxies were supposed to be messy, chaotic, clumpy collections of gas and stars, still finding their shape. But Alaknanda looks like it belongs in the modern universe, alongside galaxies billions of years older. It has 2 sweeping spiral arms wrapped around a bright, round central region. It's organized, it's mature, and it's breaking all the rules. In late 2025, 2 astronomers from the National Center for Radio Astrophysics in Pune, India, Rashi Jain and Yogesh Wadadekar, were studying images from the James Webb Space Telescope. They were examining data from 21 different filters, dissecting light from the early universe, and then they found something that made them stop. A galaxy so perfectly formed, so unexpectedly mature, that it challenged everything they thought they knew about cosmic history. Rashi Jain and Yogesh Wadadekar spend their days studying the cosmos from Pune, India. Using the most powerful space telescope ever built, the James Webb Space Telescope, they were peering back in time, hoping to understand how galaxies formed in the universe's infancy. What they found would make headlines around the world. The James Webb Space Telescope is uniquely powerful. Its infrared vision allows it to see through cosmic dust and look further back in time than any telescope before. For their study, Jain and Wadadekar used 21 different filters, each one capturing a different wavelength of light. Together, these images would reveal the true nature of a galaxy from the dawn of time. They named it Alaknanda, after the Himalayan river that serves as one of the headstreams of the sacred Ganga. Why this name? Because the Alaknanda River is the sister of the Mandakini, and Mandakini is the Hindi name for our own Milky Way galaxy. Just as the rivers are connected in the mountains, this distant spiral is connected to our cosmic home. A poetic name for a poetic discovery.
Alaknanda lies at a redshift of about 4, meaning its light has been traveling for more than 12 billion years to reach us. We are seeing this galaxy as it appeared just 1.5 billion years after the Big Bang. The universe was only 10% of its current age. And yet, here was a galaxy that looked remarkably similar to our own Milky Way, which is 10 billion years older.
In the silent depths of space, beyond Earth's familiar blue horizon, lies a mysterious red world, Mars. For centuries, Mars has captured human imagination, inspiring myths, science fiction, and groundbreaking exploration. Mars is about half the size of Earth, with weaker gravity and a thin atmosphere made mostly of carbon dioxide. It is home to Olympus Mons, the largest volcano in the solar system, towering nearly 3 times higher than Mount Everest. Valles Marineris stretches over 4,000 kilometers, a canyon system so vast it would span across entire continents on Earth. Planet-wide dust storms can engulf Mars for weeks, reshaping its surface and darkening its skies. Scientists believe that billions of years ago, liquid water once flowed across Mars. Ancient Mars may have been warmer and wetter, possibly even capable of supporting microbial life. Humanity's journey to Mars began in the 1960s, with ambitious robotic missions sent across millions of kilometers. Rovers have explored its dusty plains, drilling rocks and sending invaluable data back to Earth. Standing on Mars, the sky appears butterscotch-colored, and the sun looks smaller than from Earth. Mars has polar ice caps made of water and carbon dioxide ice, growing and shrinking with the seasons. Radar data suggests frozen water may still exist beneath the surface. Space agencies plan future missions to send humans to Mars, aiming to build sustainable habitats. Astronauts would face extreme cold, radiation, and isolation, but the rewards could redefine humanity's future. One day, Mars may become humanity's second home. The red planet continues to challenge us, inspire us, and remind us that exploration is part of who we are.
December 1972. Gene Cernan climbed the ladder of the lunar module, took one last look at the desolate beauty of the moon, and spoke words that would echo for generations. "We leave as we came, and God willing as we shall return." Then he stepped inside. The hatch closed, and for 50 years the moon sat silent, waiting. No human footsteps, no voices. Just the whisper of micrometeorites and the slow turning of the lunar dust. But the waiting is almost over. For the first time in half a century, humans are going back. This is Artemis II, the first crewed mission of NASA's Artemis program. Not a landing, not yet, but something just as important, a proving ground. 4 astronauts will climb aboard the Orion spacecraft, ride the most powerful rocket ever built, and travel 250,000 miles to the moon and back. They won't land, but they'll do something no humans have done since 1972. They'll see the moon up close, with their own eyes, and bring the rest of us along for the ride. Why now? After 50 years, why go back? Because the moon is more than a destination. It's a proving ground. A place to test the technologies, the systems, the human endurance that will one day take us to Mars. It's a symbol of what we can achieve when we work together. And in a world that often feels divided, Artemis reminds us that we're capable of something greater. We're capable of reaching for the stars. In this documentary, we'll follow the entire Artemis II mission, from the final preparations on Earth to the moment of launch. From the journey to the moon to the historic flyby of the far side. From the return to Earth to the triumphant splashdown. This is the story of the mission that brings humanity back to the moon. At the heart of Artemis II is a monster. The Space Launch System, SLS for short, is the most powerful rocket ever built. Standing 98 meters tall, it's taller than the Statue of Liberty. When it launches, its 4 RS-25 engines and 2 solid rocket boosters will generate 8.8 million pounds of thrust, more than the Saturn V that took Apollo to the moon. It's a machine of almost incomprehensible power. The 4 RS-25 engines at the base are recycled from the Space Shuttle program, but upgraded, improved, pushed harder than ever before. They burn a mixture of liquid hydrogen and liquid oxygen at temperatures so cold they'd freeze your blood instantly. The fuel is pumped at such pressure that the turbo pumps could drain an Olympic swimming pool in 25 seconds. These engines are the product of decades of engineering refinement. Strapped to the sides are the 2 solid rocket boosters, each one longer than a football field. They provide 75% of the rocket's thrust at liftoff. Once they've burned through their fuel, about 2 minutes after launch, they'll separate and fall back to Earth, where recovery ships will pull them from the ocean for reuse. Nothing goes to waste. The orange core stage is the backbone of the rocket. It holds 2.6 million liters of propellant, enough to fill 10 Olympic swimming pools. At liftoff, it weighs over 2,500 tons. Most of that is fuel. By the time it separates from the upper stage, 8 minutes later, it will be empty, falling away to burn up in the atmosphere. It's a one-use wonder, sacrificed for the mission. Above the core stage sits the upper stage, the ICPS. Once the boosters and core stage have done their job, this stage takes over, pushing Orion out of Earth's orbit and toward the moon. It's powered by a single engine, a version of the RL-10 that's been used for decades. Reliable, proven, ready for one last job before it's discarded. 4 humans, 1 mission. The first international crew to venture beyond low Earth orbit. 3 Americans, 1 Canadian. Together, they carry the hopes of not just their nations, but of all humanity. Meet the crew of Artemis II. First, the commander, Reed Wiseman, a veteran of a previous space station mission, a naval aviator, a test pilot, the kind of calm, decisive leader you want at the helm when things go wrong. He's flown once before, spent 165 days in space, done 3 spacewalks. Now he leads the most ambitious mission in a generation. The pilot, Victor Glover, a naval aviator, a test pilot, and a veteran of the space station. He'll be the one flying Orion, manually piloting the capsule during critical maneuvers. He's also making history as the first African American to travel to the moon. When he looks out the window at the lunar surface, he'll carry the hopes of millions who dreamed of this moment. Mission Specialist, Christina Koch. She holds the record for the longest single spaceflight by a woman, 328 days on the International Space Station. She's done 6 spacewalks. She's an engineer, a physicist, and now she's going to the moon. When Artemis III lands, she's in line to be the first woman to walk on the lunar surface. But first, she has to prove the systems work. And finally, Mission Specialist, Jeremy Hansen. He's making history as the first Canadian and the first non-American to travel beyond low Earth orbit. A fighter pilot, a veteran of the Royal Canadian Air Force, he's been training for this moment for years. When he sees the moon from Orion's window, he won't just be representing Canada, he'll be representing every nation that dreams of the stars. For 2 years, this crew has trained together. They've hiked through Iceland, learning to read landscapes like geologists. They've practiced emergency drills in simulators, rehearsing every possible failure. They've spent countless hours in the pool, practicing spacewalks they won't actually do, because on Artemis II there are no spacewalks. But the training builds trust, builds teamwork, builds the bond that will keep them alive 250,000 miles from home. The crew's home for 10 days is Orion. At first glance, it looks like an Apollo capsule, the same cone shape that brought astronauts home in the 60s and 70s. But inside, it's a 21st century spacecraft. Advanced computers, modern displays, a toilet, something Apollo didn't have, and enough room for 4 people to live, work, and sleep during their journey to the moon and back. Below the capsule is the European Service Module, built by the European Space Agency. It's the workhorse of the mission. It provides electricity from its 4 solar arrays. It holds the fuel for the engines. It carries the water and oxygen the crew will breathe. And at the end of the mission, it will be jettisoned to burn up in the atmosphere, sacrificing itself so the crew can come home. Inside, Orion is cramped but functional. 4 seats, 2 in front, 2 behind. The commander and pilot sit up front with a bank of displays showing everything from trajectory to life support. The 2 mission specialists sit behind, monitoring systems and preparing for observations. There's a small galley for food, a toilet behind a curtain, and sleeping bags that attach to the walls. For 10 days, this is home. On Artemis I, the heat shield performed unexpectedly, more charring than predicted. Engineers spent months analyzing, testing, certifying it for crew. Now it's ready. When Orion returns to Earth at 32 times the speed of sound, the heat shield will face temperatures of 2,760 degrees Celsius, half as hot as the surface of the sun. If it fails, the crew doesn't come home. It's the most critical piece of hardware on the spacecraft, and on top of everything sits the launch abort system. If something goes wrong during launch, if the rocket starts to fail, this system fires, pulling Orion and its crew away from danger in milliseconds. It's been tested successfully. It's ready, and hopefully, it will never be used. Flight Day 1, Launch Day. The crew straps in hours before dawn. The countdown ticks down. 10, 9, 8. The engines ignite, but the rocket holds, computers checking everything is perfect. Then the hold-downs release, and 8.8 million pounds of thrust push them skyward. In 2 minutes, they're through the atmosphere. In 8, they're in space. For the first time in 50 years, humans are on their way to the moon. Once in orbit, the crew has work to do. They'll spend about 24 hours circling Earth, checking every system. Life support, communications, navigation. If anything's wrong, they can turn around and come home. But everything checks out. Their go for the moon. One of the first tasks is a proximity operations demonstration. The upper stage, now empty, becomes a target. Victor Glover takes manual control of Orion and flies toward it, carefully, precisely, then backs away. It's practice for future missions, when Orion will need to dock with landers and space stations. In the blackness of space, with Earth below, the crew proves they can fly this machine. Flight Day 2. The critical moment. Translunar injection. The upper stage fires for about 5 minutes, pushing Orion from Earth orbit to lunar trajectory. When the burn is complete, they're committed. There's no turning back now. Earth shrinks in the window behind them. Ahead, the moon. For the next 3 days, they cruise. The routine is simple. Check systems, eat, exercise, sleep. They send video messages home, each one taking longer to arrive as the distance grows. Earth shrinks from a world to a sphere to a dot. Ahead, the moon swells in the window. By Flight Day 5, they cross into the lunar sphere of influence, where the moon's gravity pulls harder than Earth's. They're no longer Earth's children. They belong to the moon now. Flight Day 6, the moment they've trained for. Orion swings behind the moon, and Earth disappears. Communication cuts out. For 30 to 50 minutes, they're alone, the first humans ever to lose contact with Earth while so far from home. And then they look out the window. The far side of the moon, ancient highlands, basins carved by impacts billions of years old. No human has ever seen this with their own eyes. Christina Koch grabs the camera. Jeremy Hansen starts describing what he sees, the colors, the textures, the shapes. For 3 hours, they observe, photograph, record. They're scientists now, explorers, doing what humans do best, seeing, learning, understanding. At closest approach, they're about 7,500 kilometers from the lunar surface, farther than Apollo, but close enough to see details no human has ever seen. The moon fills the window, a basketball at arm's length. They're moving at 36,000 kilometers per hour. In the silence of the far side, with no radio, no Earth, no one but themselves, they are the most isolated humans in history. When they emerge from behind the moon, Earth reappears, a tiny blue dot, but growing. They're on a free return trajectory. The moon's gravity has flung them back toward home like a slingshot. No engines needed now. Just patience. For 3 days, they watch Earth grow from a dot to a sphere to a world. Home is calling them back. Flight Day 10, re-entry. The service module separates, burning up in the atmosphere as planned. The heat shield faces forward as Orion hits the atmosphere at 40,000 kilometers per hour. Plasma builds around the capsule. Temperatures reach 2,060 degrees. Communications blackout. 7 minutes of silence. Inside, the crew is pushed back into their seats by 6 times Earth's gravity. They can barely breathe, barely move, but the heat shield holds. The parachutes deploy. First the drogues, then the mains, and then splashdown. The Pacific Ocean, off the coast of San Diego. After 10 days and 2 million kilometers, Orion splashes down. The capsule bobs gently in the waves. Recovery divers approach in boats. The hatch opens and the crew emerges, tired, dehydrated, but alive. They've done it. They've gone to the moon and back. For the first time in 50 years, humans have left Earth orbit and returned safely. The door to the solar system is open again. But not everything has gone smoothly. On Artemis the Fern, the heat shield performed unexpectedly, more charring than predicted. Engineers spent months investigating, running tests, building models. They ultimately certified it for crew, but some in the space community remain concerned. The crew knows the risk. They've trained for it. They trust the engineers. But the question lingers. Will it hold? In February 2026, just weeks before launch, a problem emerged. Helium flow to the upper stage was interrupted. The rocket might need to roll back to the vehicle assembly building for repairs. The March 6 launch date suddenly seemed uncertain. This is the reality of spaceflight. Problems arise, schedules slip, and the crew waits. They train, they prepare, they stay ready. But the rocket decides when it's ready to fly. Beyond Earth's magnetic field, radiation is a constant threat. Cosmic rays from distant supernova, solar particles from our own sun. Orion has a radiation shelter, a small space with extra shielding where the crew can wait out a solar storm. Scientists busy for years. From their vantage point, the crew can see details that satellites miss. They'll focus on the Oriental Basin, a massive impact crater on the western edge of the moon. They'll study ancient lava flows, impact melt, the difference between the near side and the far side. And they'll do it with the most powerful scientific instrument ever invented, the human eye. The crew are also research subjects. They'll wear monitors to track radiation exposure. They'll perform cognitive tests to see how deep space affects the brain. They'll provide blood and urine samples to study how the body responds to the deep space environment. Every piece of data helps prepare for Mars, for longer missions, farther from home. During the mission, Orion will deploy several small satellites, CubeSats, that will study the moon and test new technologies. Some will look for water ice. Others will test navigation systems. Each one is a stepping stone to something bigger, a proof of concept for future exploration. Why does this matter? In a world full of problems, climate change, conflict, division, why spend billions to send 4 people to the moon? Because exploration is what we do. It's who we are. When we look up at the night sky, we wonder. We dream. We imagine what's out there. And then we go. Not because it's easy, but because it's hard. Because the challenge makes us better. Because the journey teaches us something about ourselves. Reed Wiseman says they're doing this for everyone back on Earth. Victor Glover thinks of the children who will watch and dream. Christina Koch remembers the girls who never saw themselves in space, until now. Jeremy Hansen carries the hopes of a nation, and of all nations. 4 humans, 1 mission, representing all of us. 50 years ago, we left. We said we'd return, and then we didn't. The years passed. The astronauts aged. The memories faded, but the dream never died. And now finally we're going back. Not just to visit, but to stay. Not just for ourselves, but for everyone who ever looked up and wondered. Artemis II is the first step, the next giant leap, and it starts now. Thank you for watching. If this journey inspired you, share it with someone who needs to dream. Comment below. What does the return to the moon mean to you?
Imagine a volcano so massive that it would cover the entire state of Arizona, so tall that its summit would be 3 times higher than Mount Everest, so wide that its base stretches 600 kilometers across the Martian landscape. This is Olympus Mons, the largest volcano in the solar system. A shield volcano of such immense scale that it defies terrestrial comparison. Located in the Tharsis region of Mars, this giant has been extinct for millions of years. But its features tell a story of volcanic activity that shaped the red planet and holds clues to Mars's watery past. This is the story of Olympus Mons, the giant that towers over Mars. Why does it matter to planetary scientists? Because it represents a volcanic end member, the extreme of what shield volcanoes can become. Its low gravity, stable crust, and long-term hotspot activity allowed it to grow to impossible proportions. But beyond its size, Olympus Mons holds mysteries, the steep cliffs at its base and the surrounding aureole deposits, and the possible role of water in shaping its unique features. Understanding Olympus Mons helps us understand Mars itself. NASA states, with a base that sprawls across 373 miles, the shield volcano rises to a height of 17 miles. In this documentary, we'll explore every facet of Olympus Mons, from its staggering dimensions to its volcanic origins. This is the complete story of the solar system's largest volcano. Let's begin our journey. Let's start with the most staggering number, height. Olympus Mons stands 27 kilometers above the surrounding Martian plains. To put that in perspective, Mount Everest is just 8.8 kilometers above sea level. You could stack 3 Mount Everests on top of each other and still not reach the summit of Olympus Mons. Its peak rises so high that it actually extends above most of Mars's thin atmosphere. But height is only part of the story. Olympus Mons spans 600 kilometers in diameter, roughly the size of the state of Arizona. Its base is so vast that if you stood at the edge, you couldn't see the summit. It would be hidden below the curvature of the planet. The entire Hawaiian island chain, from the Big Island to Kauai, would fit comfortably within its footprint. The volume is almost incomprehensible. Olympus Mons contains about 100 times more material than Mauna Loa, Earth's largest volcano. Its sheer mass has actually depressed the Martian crust beneath it. The volcano is so heavy that it has created a flexural trough surrounding the entire edifice. Unlike the steep cones of stratovolcanoes, Olympus Mons is a shield volcano with remarkably gentle slopes. The central part rises at an angle of only 1 to 5 degrees. So gradual you could walk up without noticing the incline. But at the edges, everything changes. The periphery terminates in steep cliffs that slope 12 to 28 degrees, dropping 8 kilometers to the plains below. Olympus Mons is a shield volcano formed by the eruption of low-viscosity basaltic lava, a broad, gently sloping profile. Over millions of years, layer upon layer stacked up to create the massive edifice we see today. Eruption rates were similar to those observed in terrestrial hotspot volcanism. Olympus Mons likely formed over a long-lived hotspot, a plume of hot material rising from deep within Mars's mantle. Unlike Earth's moving plates, Mars's thick, immobile crust allowed the volcano to remain stationary. This is why it grew so large it never moved away from its magma source, feeding from the same hotspot for billions of years. Mars' gravity is only 38% of Earth's. This lower gravity means that lava can build higher structures without collapsing under their own weight. On Mars, the reduced gravity allowed Olympus Mons to reach heights that would be impossible on our planet. Gravity simply